Datastax is a generative AI data company that provides tools and services to build AI and other data-intensive applications. Ed Anuff is the Chief Product Officer at Datastax. He joins the show to talk about making Apache Cassandra accessible, adding vector support at Datastax, envisioning the future application stack for AI, and more. This episode of Software Engineering Daily is hosted by Sean Falconer. Check the show notes for more information on Sean's work and where to find him.
Ed, welcome to the show.
Thank you.
Yeah, thanks so much for being here. I'm glad we were able to pull this off. And maybe we can start with an introduction. Who are you? What do you do?
Sure. I'm Ed Anuff. I'm the Chief Product Officer at Datastax.
I think Datastax is a really interesting company. It's been around over 10 years now. And as sort of an outsider, looking in, I feel like the company itself has kind of managed to reinvent itself maybe a few times along the way, which makes sense for you want to stay relevant in a technology company. You always got to be kind of like iterating and moving with the times. But starting with building services on top of Cassandra and to real-time data, and now I think a heavy focus in AI. Can you give a little bit of background on the company and some of the product history there?
Sure. So we are the company that has been the main sponsor of Cassandra, which is, the scale-out database originally created by Facebook that's used by a lot of folks who are just trying to handle very large amounts of data in real time. And from that perspective, it's made a ton of sense for us to be really keeping track of or keeping abreast of where people are using data and figuring out how to make it relevant to whatever sorts of applications that they're building. Over time, that's involved a lot more machine learning and AI type use cases.
Yeah. I mean, data is really the fuel, or I say sometimes the love language of AI. So it really starts there. But in terms of, when Cassandra sort of spun out of Meta and was released as this open source project, like if I'm a company and I want to just run Cassandra on my own, like what is hard about doing that on my own versus going and using, working with a company like Datastax?
So first of all, many folks do run it on their own. That's the great thing about open source. I'd say the first thing that becomes really challenging is the fact that it is a distributed database, right? So most of us in our experiences with databases are not actually using distributed databases, like whether we are using Postgres or MySQL or even, God forbid, Oracle, or you're using something like MongoDB. Like these are mostly fairly monolithic databases. Like I got a server and I install the database in it and I run it and everything's good. Cassandra is a distributed database fundamentally at its core. And what that means is that you have more data or you need to serve more requests, you add more nodes, which is a really powerful thing to have. And in fact, you're not going to run an internet scale service without that. But operationally, now you're talking a distributed database, right? And most developers may have had experience in doing distributed compute. Most folks, if they can help it, are using something like Kubernetes or what have you. And in fact, most developers actually sit on top of that and use some sort of platform as a service that handles all that complexity. But that's a pretty big step function for database. And because of that, particularly for companies that weren't used to doing, DevOps or, cloud operations, they really saw a lot of value in going to a company like ours that just packages all that stuff up and gives you this turnkey control plane. In fact, in many ways, a lot of this preceded things like Kubernetes. In fact, over the last few years, we've done a lot of work to make Cassandra play really well with Kubernetes and other types of, cloud management tools. But if you think about it, like when Cassandra came out of Meta, like, they put the database out there, but think about sort of where you were 10 years ago, like this idea of having a farm of servers that, were handling state was kind of a new idea for most folks.
Yeah, absolutely. And even, with that sort of analogy around distributed computing in Kubernetes, like, as you mentioned, like most people are probably not managing their own Kubernetes clusters. They're using a managed service on top of that to abstract away some of that complexity. And then you throw something even, newer, harder concept that a lot of people are unfamiliar around, essentially a distributed database. And then it makes a lot of sense to go with essentially someone who can abstract away some of that complexity.
And again, the way I look at it is there's plenty of folks who are deep into that. And, open source Cassandra is thriving. We just shipped 5.0. It's great, like a lot of options for people. And it's been about 15 years since the open sourcing of it. And it's still like, I talk to startups all the time that are like, yeah, no, we had massive data set. We're using Cassandra. It still is it's the only game in town. Like if you don't want to be locked into something from one specific cloud vendor. So,
right. Yeah.
A healthy community, really robust technology. Like we're not just the only contributors to it. Folks like Apple and Netflix and others, really heavy contributors into keeping this thing state of the art.
In terms of like companies' evolution and adoption of, either Datastax or Cassandra directly, are people sort of building with that level of scale in mind as a scale up startup, or do they hit a certain point in maybe the growth of their company where they start to hit scale issues, some of this complexity around scaling maybe more of a traditional sort of monolithic database, and then they start to go and look for alternatives that allow them to do this essentially in a distributed fashion?
Sometimes it depends on what they're doing, but definitely scale is a day two concern, right? So what we've tried to do, and it's been a big part of our product strategy over the last 4 years now, and I'm really happy on how far we've taken it, is we've gone and said, look, let's not make it a trade-off. Like, let's not go and say, oh, well, only use this if you've got a lot of scale and otherwise go and use something else. And we went and looked at all the things that made it hard to use, because I think that was the historical thing, was that we were really very focused on going and saying, how can we go and handle like you're going to launch a new social network, you should be using Cassandra, right? Like that was the way we were thinking about it, right? And that's great. But then a lot of people would be like, well, maybe someday, but right now I just, I'm just trying to get this thing out the door. I just want to build an MVP or what have you. And so what we said was, that's perfectly reasonable. Let's make this thing as dead simple, as turnkey as possible for people that just want to do it wherever they are, wherever they're building around. So the good news is that when you look at it today, if you have some inkling that you're building something that a lot of people are going to want to use, you don't have to go and say, well, I'll cross that bridge when I get there. Like, you can get started. We've got the cloud service. Open source is a lot easier now. All the stuff is in there. The trade-offs, you're really not having to make a hard trade-off. But yeah, I mean, the way you put it was exactly right. That's the way a lot of people, when I would talk to developers, and I've been using Cassandra for a long time now, like even myself, where I would go and say, okay, is this a simple app that I'm building, or is this something that, I want to be a big deal sometime? And you can't always tell up front which is which. So the goal is right now is just, we're just as easy to use as anything else out there, and then you won't outgrow it.
Yeah. And I guess I think if you look at something like containers and distributed computing to the movement towards Kubernetes, I think it's gone through a similar transformation. It's basically a little bit ahead of probably the same transformation that's happening in data. So this might become sort of more of this, you fast forward 5 years, 10 years, everybody's, building this way from day one if you plan on building a growth stage startup at all.
Yeah, I definitely think so. I mean, I think that compute is always a little bit further ahead from data, but scale out compute now, like 5 years ago, everybody was like, well, why do I need Kubernetes or whatever? Actually, a little more than that. But now it's like, oh, I've got this thing, and I've just, I've created a container image, and let me throw it into Elastic Compute Service or something like that. It's very simple. Like, it doesn't get much easier than that. And you also don't worry about scale. And so the same thing is happening with data. And I like to say we're part of that, which is to say, can we make the scale out part work in a way that doesn't have too high of a operational complexity? And I think a lot of folks are coming from that direction, because ultimately what you want to do is have this very elastic approach to whatever you're doing, whether it's compute or data. And so you need the same underpinnings on both.
I think sort of that vision of things makes a lot of sense, sort of aligned with now the investment in large language models and the things that we're trying to do there, because you're talking about massive amounts of data in order to train these things. So I guess what is Datastax doing in the context of AI? Where do you see it sort of fitting into this new emerging LLM stack?
It fits in a couple of different places. Obviously, you look at a lot of folks who use Cassandra, as a staging database for things like training and so on. But where we're predominantly being used is as part of these RAG applications. And to some degree, that's true of all of the, well, I wouldn't say all of them, but all of the databases that are worth using are seeing that they're playing a pretty important role within RAG applications. But Cassandra has the advantage in that a lot of the data that people are serving at their user experience tier, that is also the same data that they want to use within their RAG applications. And so we're seeing a lot of that. And we've definitely seen it over the last year and a half. And like, for example, for our cloud service, more than half of the people that sign up for it are doing some form of RAG application that's using vector retrieval, right? And you can actually do RAG without vector retrieval, but just more than half of our signups, when I go and look at the data, they're actually using vector retrieval, which is pretty cool. That definitely was not the case a year ago. It just shows like how much activity is around this in terms of people trying to build these types of apps.
Yeah. I mean, I think a year ago, most people didn't know what a vector was. So
right. Yeah, the timing has been pretty interesting. But I mean, people started really, I think like the year before last, most of us that were following this stuff pretty closely were like, okay, vector embeddings and doing vector-based retrieval out of your data sets, some sort of similarity search is proving really, really interesting. Now, of course, it took the LLMs to be able to generate, because you need these embedding models to generate the embeddings that then allowed you to do a reasonable search. But the thing was that even the publicly available embedding models back in 22 were already good enough that you could build a better search engine with vector search. So a lot of folks, us included, were already building towards vector search retrieval, even without the idea of the sort of chatbot interface. And that's why you had folks like us doing what we were doing, and Lucene had its HNSW implementation, and you had various folks. And it was the reason why you had like even these folks like Pinecone and Weaviate and so on. It wasn't like everybody got up and said, hey, I'm going to go and build databases for building RAG applications with large language models. But this idea of doing a vector-based retrieval of data in the database using embeddings was already something people were thinking a lot about. So, and in many ways, like when RAG appeared, that was more of a adapting that work. Like I said, like vector search was something that had been going on for a few years, actually for a lot longer than that, but like in practice for a couple of years. And at database companies and so on, like 21 and 22, like that was always like a big part of our roadmap. And I'm sure it was the same for other folks. And that's why as we got into 23, you saw that in addition to sort of the people who only did vector retrieval, you had folks like us come out very, very early in the year with our vector retrieval stuff. And you had, over the course of the year, you had others like Mongo and OpenSearch following. It's just because a lot of this activity was already underway with that convergence.
Mm-hmm. Yeah, that makes sense. I mean, there's now over, I think, at least 60 different databases that offer some form of vector support, from the specialized vector databases to, your Postgres's of the world and so on.
I would hope so. I would hate to have a data. But the funny thing is there actually are some that, like, I marvel at that, but I've seen a couple of these databases that just recently, like in the last 3-6 months, since the start of the year, added vector as it was this new thing. And I was like, well, I'm glad to see that. Like, I can't imagine having a database people would want to use that didn't have a really strong vector native data type as one of your retrieval things. Now, that said, it's not the only way to retrieve data. And if you look at what a lot of people are doing with RAG, they're combining vector with additional terms in other columns and stuff, and we can talk more about that. But it certainly is like a foundational capability that you need to have.
Yeah. I mean, it's going to be the standard, basically, just like you support, like a varchar in a date time field. One of the things that you said a few minutes ago that I want to go back to was, I think you were talking about how you saw this pattern essentially with the people using Cassandra, where they maybe are using that as essentially their, transactional database for their application. But then the data that they're collecting, they also want to leverage for LLMs and other probably AI applications. So rather than kind of thinking about those two different worlds as like completely separate things and having a completely different like data pipeline, if you have sort of one platform that can manage all of that, then it's probably, you can keep the data where it is basically, and it's an easier transition. Is that essentially the idea based on that pattern that you're seeing from these folks?
Yeah. I mean, I'd like to imagine that everybody's seeing what we're seeing. Hopefully we're seeing it a little more clearly than others, but that's the usual thing about, infrastructure and architecture is you want to make sure you're getting the patterns right. Like, we're not trying to go and say, like, you should build it this way and the rest of the world is over here. The thing that we're seeing is that not everybody is doing RAG the same way right now. And what I mean by that is that a lot of people are doing very first generation RAG stuff. And what that largely consists of is, and a lot of folks have sort of the shorthand for that, they just call it chat with PDF, PDF documents. And what that is, that's basically your hello world of building a RAG application, which is to go and it's not a bad place to start. Like, if you're a developer and you're trying to figure out, like, what's this RAG thing all about, that's what I would recommend, because you probably have a whole bunch of PDFs that, you have, or that, your company has, or whatever. And you just throw a bunch of them in a folder and you use, some off the shelf stuff to go and read those in, chunk them, because you gotta turn them into chunks of data that will, one, fit within the context window of the LLM, but two, will represent a discrete semantic conceptual block, meaning that you want all of the text that you're grabbing ideally be like a paragraph, because when you reduce that down to a vector, you want that vector to encodify the concept that best describes that chunk of text. And so when you talk to people who are doing RAG, you hear this chunking thing a lot. And that's frankly a lot of trial and error data engineering, which is like, I'm taking my source data and turning it into these chunks. And that's great. Like, people can spend, like, we talk to businesses and stuff, and they can spend 6 months learning the tools of the trade to just get that basic chunking and knowledge retrieval. But when you're done, what you have is you basically have a better search engine, and you can put sort of a chatbot UX around it. And by the way, in some circumstances, that's extremely cool. But what we're finding is that in practice, you want to do a little bit more than that. And what you want to do is sort of move to the second generation of what you do with RAG. And that starts to involve multiple sources of data beyond just sort of, let me chunk up this knowledge content.
I think too, back to the chunking thing, even that gets really complicated, especially, if you have a table, like, how do you chunk the table in a meaningful way? I mean, and there's companies that basically, that Unstructured and a handful of others that.
Yeah, like Unstructured is awesome. Llama Index has been focusing a lot on that particular problem. A whole bunch of other folks. Like I said, that's one where, in fact, I think for people that are doing RAG, the chunking problem ends up being the most unfamiliar piece, just new to what they're doing. And so you lose a lot of time in just learning, how do I do chunking right? So the thing about RAG is most people have this idea of they use the prompt and they use context interchangeably, right? And we generally have this mental model, which is like, I've got my LLM and I put this input into the LLM, and that's typically called the prompt, although properly speaking, the prompt is a component of the context. And you put that into the LLM and you get a response. And what RAG says is, I can take that question and maybe I actually use that question itself that I go and ask, like, what's the best place to go to lunch? And I take that, and before I give it to the LLM, I actually do a separate thing, which is I take that question that you asked, Ed, and I turn it into a vector, and I do a query against a known set of data. And that known set of data is those chunks that we just talked about, right? So now I maybe have all of these restaurants, and I've got restaurant descriptions, and I've taken every one of those restaurant descriptions, and I have turned it into a vector. And I've taken that question that I asked, which is, where should I go to lunch if I want a really great burger? I've turned that into a vector. And I run through the database and I compare those two vectors and I get the ones that are most close to it. And so now what I have is I have a set of relevant data that maybe is this set of great restaurants here in San Francisco that I've gone and done. And I've done that vector comparison. That's a similarity search. So now I have this set of data before I even get to GPT-4, for example. here's this set of stuff. Further, when I go and do that retrieval, because I'm doing it off of a vector database like Datastax, that allows me to combine that vector similarity with maybe with a geo query. So it's not just like, hey, what's a great place to get a great burger, but within half a mile of where I am now. And so I have that set of data and I've got the original question. And now what I do is I take all of those and I put them into a context. And that's what I go and give to the main LLM, what I give to GPT-4. With an additional thing, which is my system prompt, which goes and says, hey, the user asked this question, and when you prepare the response, use his question as well as this set of data that we retrieved, that we've pre-retrieved and we know is relevant to his question. And so now the LLM is going to prepare that response, and what it's going to do is it's going to draw really heavily on the content that we supplied it in that context, right? And so then it knows, the LLM knows everything it's been trained on, but it also has this specific data that is now like personalized, because remember, we did that geo retrieval, and it's also perhaps some special content that's not on the web. Like maybe we've got this database of restaurant reviews that we could draw on. And so now the question, that the response that the LLM gives back is grounded, because this data came from the database, it's personalized, and that's where the retrieval augmentation of RAG comes from, right? That's that pre-retrieval that I did, I'm now using to augment that generation. And so that's what RAG is all about. And a lot of people are just doing that very first generation stuff, which is like, let me just return some stuff from the PDF. But those additional pieces that I threw in there, like my geographic location, or maybe my personalization, right? Like we have people that are building recommendations for vacations, for travel. And like you start to do that, and now you're getting something that isn't just sort of going to the memory of the model, but it actually is now like really knowledgeable in it, or at least the responses that are generating are really knowledgeable about a specific domain. So a lot of that comes from pulling in more data than just those. The chunk data is important. That's like the knowledge piece, but you can add like personalization, and you can add a lot more data from other sources. So that's kind of what we're seeing, is that the more advanced folks are doing. Yeah. And I think you go like a year from now, and that's where the majority of folks are going to be, because doing like a thin layer just on top of the model, like retrieving some static content, is interesting, but it's not super compelling.
And the advantage there, as well as some of the things that you mentioned, is it's up to date, where a foundation model is basically fixed in a certain epoch. So if you want to do anything like this for like in a e-commerce retail use case where products are changing all the time, then you need to essentially combine sort of traditional database type of search. So I know that the products are actually in stock, available, like for my location, all that type of stuff, along with being able to combine that with like similarity search, so that if I'm looking for blue shirts, but maybe there isn't blue shirts available, I can get like the next best thing, which is like a purple shirt or something. I want to have that level of flexibility in the results that I'm feeding into the LLM.
Yep. And that's a little bit of like why we talk about a lot of this stuff, because a lot of companies use Cassandra for that. It just ends up being one of the types of things that Cassandra is really good for, is let me have all this stuff, but let me have it like all my products, but in inventory and what's close by. Like, for example, when you go to Home Depot and everything in the app, and it tells you it's in that there's 25 of this thing, in aisle H7, like that's all a Cassandra query.
Mm-hmm. So is AstraDB essentially the vector version of
AstraDB? Yeah. So AstraDB is our cloud service. And so what we've done is we've taken all of these things and we made them really as easy as possible to use. So it's a vector-based. So we have vectors as a native data type. We built that at a very low level within Cassandra. So you have a lot of performance. We, in fact, open sourced that as something called JVector. And so we're really happy on that. But Astra makes it very turnkey to use. You can just sign up as a cloud service. You can have your database ready to go in 10 seconds. All the good things you would expect. But behind the scenes, you have all of this power and scale.
Mm-hmm. So what was involved with introducing that vector type? Like, what was sort of the scale of that project in order to be able to extend Cassandra in that way?
So a couple of things. First, we had been doing a lot of work for a number of years in improving the indexing system of Cassandra. And the reason why is because we are a NoSQL database. And a NoSQL database, like when you think about how do I find data in a database, that's really one of two ways. One is the relational model, meaning that like, oh, I have a customer ID and I've got the customer record and I want to find all their orders. So I go from here, look up the customer, get the customer ID, and I just do that as a relational query, right? The other option is you have a very robust indexing system. And so that's the approach that NoSQL databases like Cassandra, Mongo, and others have taken, which is to go and say, hey, we can have a much more performant database with a much more developer-friendly data model, but what we're going to do is we're going to give you a more powerful indexing system to make that possible. So we've been rebuilding the indexing system really for sort of the last 5 years. This major effort in the project. And as part of that, we made the whole system where we had data types extensible. And so what this allowed us to do was, very quickly go, and so this was early last year, we wanted to add vector capabilities. And what we did was, we did the same thing, by the way, that most of the other vector databases did, which was our first generation was using the, HNSW, Hierarchical Navigable Small Worlds, vector similarity search that originally was created, at least the vector comparators and such, were created as part of the Lucene project. And that was the same thing that pretty much all the other databases did, whether they were quote unquote pure play vector databases or others. And the first generation that we put out there was based on that, which, by the way, was a good answer, but what we found wasn't a great answer. And so we followed that up in fairly short order, relatively speaking, so we did that first iteration and we had that in like March of last year. And then around September of last year, we switched to JVector, which is our implementation of disk ANN. And so disk ANN, the advantage, and as the name would imply, is designed to do much better where you're actually doing disk storage-based usage of the indexes. There were a lot of things within the HNSW implementation. We're just assuming that things were all in memory. We needed to be able to do a scale-out implementation. And so that's why we adapted that, and we released that as open source, standalone open source project. That was done by Jonathan Ellis, who was, one of the main founders of the Apache Cassandra project. He was the co-founder of Datastax. He personally worked on that. This was a pretty big deal. Like this release of JVector was one of the trending projects on GitHub for a long time. It's being adopted by OpenSearch now and others. And so this is what gave us the sort of the performance and the relevancy and recall that we were looking for. Now, we're actually in the process right now of taking that and actually layering something on top of it called Colbert, which actually does even better retrieval. But it's just been an ongoing thing for us, and you're going to see continuous iteration on this stuff. Like vector-based retrieval has been a thing within databases for a while now. Like people have been talking about this stuff, since the 90s, and probably, at least I've been directly involved in that stuff, but I'm sure it goes way back before that. But, just major activity as sort of a primary data type. And you're going to continue to see that for some time to come. Now, one of the things that was really important that has been an area of some debate, which is, do you just use a vector database or do you need what's called a hybrid database? And we obviously think you need a hybrid database. And the idea is that, like going back to my example of the GeoQuery, like I want to be able to go and say, here's this question asked, give me all the restaurants that, have a great burger, and I do that vector query around it. But I also want to say, and within, half a mile, of this latitude, longitude coordinate, right? And so I want to combine those in a single query. Now, by the way, in that example I just happened to give you, it's kind of interesting. That second thing is also a second vector query, happens to be a two-dimensional vector query rather than a 1500 or 1536 coordinate vector query, but you're actually doing two different vector comparisons and merging those results. That's the type of thing that you want your database to be able to do. And so at a certain point, like this idea, is it a vector database or is it a hybrid database, which is, I'm not sure is the best term, but that's what people are calling, meaning does it do traditional database results and vector database results? I think most people will lean to this idea that I'd rather have more of this data in these records and be able to query by multiple, essentially multiple criteria.
Yeah, I mean, I think there's certain use cases, like some of the ones that we spoke about, that are pretty difficult to solve for unless you have sort of this hybrid approach, because sometimes you need exact match or, a bounding box match, not necessarily sort of the, nearest neighbor type of search. In terms of the HNSW versus JVector, like what was the like limitations of HNSW that you ran into, and how did you essentially, move beyond that? Like what is the advantage that you're getting using JVector?
Well, I won't do all of the justice to this, but we started to see the breakdown on larger data sets. What we found was that, everybody does a reasonable job when you're dealing with small data sets, to the extent that a lot of folks, like you read on Hacker News, and they'd be like, why are you even using a database? I'm doing all my vector retrieval in memory, right? And, which was like true. It was like if you had a couple of thousand vectors and you were just trying to do like a very fast similarity search on them, like you could do it in memory and it'd be just a much better place. And what we started to find was that people would come in and they'd start off and they'd get really great results, and then they would start to load much larger data sets. And so what we found was that you very quickly, at least within HNSW, and again, your mileage may vary around this, but what we found was that we started to get into, at least in the stuff that we were seeing, and this was mid last year, we started to see that you'd hit a wall that would directly start to impact the relevancy of your retrievals. And not to mention, of course, there were performance issues that were also pretty significant. And so that's why we started looking at disk ANN and doing an implementation around that. And, it worked out very, very well for us. And I'm pretty sure at this point that most of the databases that are fairly serious about vector as a use case have moved beyond sort of the original HNSW approach. Again, it was our starting point for everybody. Like, I don't want to name names, but like everybody in the industry was doing some variant of that because it was the main public domain, open source, not public domains, but open source reference implementation that people would look to. And so that was kind of your first order implementation of it. And now that's where most people are. I forget the name of the one that Google's using, a slightly different one now in their databases. But, for example, I think Microsoft has moved to disk ANN as well for their stuff. And then, our JVector implementation is just, we said, look, from an open source standpoint, people look for high quality reference implementations. And we wanted to, for one thing, we wanted to make sure that open source Cassandra again, yes, we want people using our cloud version, but we wanted people like going and saying, which database should I use? And we wanted Cassandra to have the reputation for being a really great vector database. So that necessitated us open sourcing that implementation anyway. But we chose to package it up in a way that we said, let's make it easier for other projects that are struggling with this to adopt.
Mm-hmm. And in terms of like when people start to run into performance issues, is that typically down to like how they're building the vector indices, or is it related to what they're using potentially for essentially vector similarity comparison, or maybe it's a combination of these types of things? Like what is that essentially bottleneck that people run into?
That's a good question. Well, let's split it out a little bit. So right now, I think that there's definitely a performance continuum that people see in terms of just their data set size. And that is a problem. Most users experience that in terms of cost, because that's at this point how I'd say sort of most of the kind of the issue is. Well, let me explain why that is. So depending on your implementation, it's going to translate into your compute cost, which, since the majority of folks doing this stuff are using some form of cloud database, what that means is that different size data sets and different vector implementations are going to chew up compute. And I'm not even talking GPU. I'm just talking about because most of the databases are not using the GPU for the vector comparison. They're using it in different places for like embedding generation and such. But what ends up happening is that different implementations, because they have different levels of compute intensivity, and obviously the cost gets passed to you as a developer, right? Like your cost per query. So what will end up happening is I've got a very large data set of vectors and I throw it into 3 different databases and the bill ends up coming back very differently. So that's your first problem. And I'm not trying to do a commercial. My recommendation would be like, try these things out and see what happens, and you're going to see a different result. I think we will do pretty good in that, right? That's why we have a business, because we do pretty good in the comparison. But my recommendation would be like, US developer building these things, you should test these things out. The second piece, though, let's assume you get within your sort of cost envelope of what you want to see. What you start to see is, particularly with the size of the data set, you start to see that your relevancy ends up sort of falling off a cliff. Because what ends up happening is, and I was alluding to this earlier, which is that the different algorithms will do a better or worse job with matching what you're doing to other clusters of close by vectors. And so what will end up happening is I'll ask that question and I may get a bunch of, like I won't really get the ones that are the closest. Or if I do that, because typically I'm like asking for like 5 at a time or something. And maybe there'll be something better that's not in that set that I got. And there's different ways to score that. And you've got your F1 scoring and such that the people use, because you've got your relevancy and your recall, like how relevant is it? And then just, did it fit into did it just work? Did some elements that should have been in there just not get recalled? And you're going to start to see those differences. And then the knobs for turning those may have different cost considerations at the database tier. Now, the other knobs that you have to turn around that tend to be 2 other things. So one is, how effective was your chunking strategy? Because a lot of this is garbage in, garbage out. And if I do very naive chunking, I'm also going to have really crappy relevancy, right? Because if that chunk has more than, a very small number of central concepts, then maybe I don't get the right piece, right? And then the second thing that will also screw me up, or want to screw me up, but can have a lot of variability, ends up being what embedding model I use, right? So those end up being different factors. All of those, so going back to your original question about performance, so your performance becomes one issue, like how well did it perform? And that typically is like, how well did it perform at a certain cost level? In terms of just, let's say, sort of raw wall clock performance, queries per second, against a certain data set, right? But then what you find very quickly within these projects is it's not just that. It's like, and then how good were the results? Like, I did this thing and was I getting crap results back? Or was I like, wow, it did a great job and really nailed it in its response? And those two end up, being related to each other to some degree, and then of course there's the third piece, which is whatever I do there, I throw into this language model, which can also have a lot of variability in what it does with it. But when we talk about performance, and I went a little long-winded there, but it's just like, this is what trips people up on these projects, is that performance is multidimensional.
Right, yeah. And in terms of, given that Cassandra is a distributed database, then how does essentially the sharding work in the world of vectors? Like, what is the partition key, and how do you figure out how to group similar vectors in a way that's going to satisfy the search, so you're not essentially having to, visit multiple nodes?
You essentially are sort of creating a hyperring. I mean, you've got each node has to go, and, each individual node ends up having its own vector space, and you've got the, and you still end up having to go and do a lot of sort of merging and stuff at the coordinator node that handles the query. It's a variation of the same problems you have with distributed queries, but it does get a little bit more complicated. We actually will be, in a future version, actually doing vector-aware partitioning. Right now, we don't. And it's not a problem, but it's an opportunity to actually do something that's a lot more interesting.
Yeah, especially as these, like, the requirements around like vector storage scales, if you're talking trillions of vectors or something like that.
Yeah, the issue becomes that, so remember, distributed database like Cassandra ends up repartitioning and rebalancing, based on certain operational conditions, nodes being added and so on.
Right, like a red factory.
Yeah. And so what you don't want to do is have to sort of, vector comparisons are expensive. So you don't want to have to go and trigger thousands of vector comparisons every time you rebalance the node. It's one of the reasons why we're being a little bit careful on how we think about these things. But you're going to see a lot of cool stuff around this stuff. And again, I'm not the person to do it justice. And in fact, Jonathan is Ellis, probably like, he's going to call me up after this and be like, Ed, you completely misstated that. And so you may want to do a follow-up with have him on, and he can get into very low-level detail on some of this stuff. But the point is, like, suffice to say, like, this is like an area that anybody that's doing a database now, it's quickly become like your primary consideration as you're thinking about this stuff.
No, this was super fascinating. And of course, I'd love to nerd out with John and talk about
Yeah.
more in depth even about vectors. But, as we start to wrap up, is there anything else you'd like to share and sort of what's next for Datastax?
Yeah. Well, so a bunch of stuff. Like, one of the main things that I think we could have talked more about, and we probably should talk a little bit more about, is the application stack. Because everything that, a lot of this, and I love geeking out on at the vector level. And the reason why all this is interesting is because people are building a new type of application, and they're building these, AI RAG applications or knowledge apps or whatever you want to call them. Like, people are still figuring out the term for it. But like, this is, last time we had something like this was when people discovered 12-factor apps back in like the Heroku days, right? Or mobile apps, right? Like, it's a new application template, and databases are interesting, and, but what makes databases interesting beyond all the things we just talked about, and actually what really makes the difference in databases, is what's happening at the application tier. Like, right? Like, everybody uses Mongo today. Love for them to be using Cassandra, but why are a lot of people using Mongo? Because what ended up happening was about 15 years ago, suddenly people started using dynamic applications that were built on JSON data and documents and stuff, right? And so you ended up having like these JSON document, you had JavaScript on the client, you had JSON on the wire, you had JavaScript on the back end, you had this data type. And so it made sense to go and say, let me have JSON on the database, right? And 10 years before that, or 15 years before that, you had people going and building Java applications that were all these ORM systems, object relational mapping, that needed SQL databases. And so people were using Postgres and MySQL, and then they were building client server and all that stuff, right? So if you want to know where a database is going to go, you got to look at this application stack. And so for all the stuff that we talked about right now, like, we spend as much, if not more time going and saying, what's the application stack for AI, and working with folks like LangChain. And we have an open source. We recently acquired a startup called LangFlow that makes a flow engine for LLM apps with Visual Tool and all this stuff that, and so this whole AI stack is really like the most important thing to pay attention to. All of the underpinnings of how do we do the retrieval and stuff, like, a lot of important stuff there, but that is all influenced by how are people building these apps, right? And figuring out, like, how can we figure out what is it that they're building, and how can we optimize how we organize the data, but how we make it possible to access that data in a way that naturally maps to these AI app patterns. And so that is an equally important topic. Like, the vector database piece, I love spending time on it because people are still learning what that means. But yeah, this is where most developers are sort of, trying to wrap their hands around, is like, okay, I want to build one of these things, and I've got this framework, and I've gone and downloaded LangChain, and like, what do I do, right? And so that's what we're trying to solve for.
Yeah. It's also, I think, the way that you differentiate at the database level is by showing sort of the art of the possible at the application level. Like, are you able to essentially enable something at the application stack that no one's been able to do before? Because when it comes to demoing a database, like, what is the demo? You run a SQL query and like, wow, I saw that 30 years ago against an Oracle database as well. Like, it is not like a compelling story there. The compelling story is like, what does this enable you to do that you couldn't do previously in terms of creating an application that actually serves a real need for people?
Yeah, no, exactly. And so that's the piece that, again, I'd love to come back, talk to you a little bit about that stuff. I think that's, again, where a lot of the action is.
Yeah, absolutely. Sounds great. Well, Ed, thanks so much for being here, and hopefully we can do a follow-up to dive into that topic as well.
Awesome. Cool. Thank you.
Cheers.